Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So welcome back. So this is a part 2 of our class today. So our chapter now is on a phase system. Okay. So what we have seen in the first session is basically this thing. So in a frequency domain, so what we have is actually in time domain, you have a convolution. In frequency domain, you will have a multiplication. And because of this multiplication of a complex number, so what is the effect? The effect is magnitude is a multiplication, still multiplication, but the phase is actually a summation. So whatever the phase in your input signal and in your system, so it will be sum. Okay, so that sum results will be on your output signal, right? So this is actually so we have developed this concept. So then, and we have seen some roughly some example, okay, not in detail, but I already showed that what will happen if the effect of a magnitude and phase. Okay, magnitude is you do multiplication, so you can do a reduce, or you can increase, or maybe you can remove amplitude. Okay, so magnitude will affect the amplitude in time domain, but phase, it will affect a delay, right? And we have seen three type of a phase system. So the first one is a zero phase. If you have a symmetry signal, so then if you have a zero phase, means that there will be no delay at all at output. Okay, so but if it is a linear phase, you will have a delay, but it is a consistent delay, which is okay. And it is good because the linear phase system is causal. So we can have a causal system. So instead of a zero phase, so it is non-causal. Other than the two, zero phase and linear phase, so we will have a non-linear phase, right? And actually, IIR filter, so actually most, maybe all or most, accept some very special system of IIR. So the system is actually non-linear phase, right? So that's why this FIR have another advantage compared to IIR, because for FIR, so we can have a linear phase. So because a linear phase is, there's no phase distortion, because the delay is consistent on every frequency. Okay, so now we're going to look at, we will work out on a real example. Okay, because previously I just show you some plots. So where's the delay happen? So where's the amplitude is reduced? So now we will do a real example, a real calculation. Okay, so we will do some workout. So let's see. Okay, this is let's say an extra example. And this is actually quite important, because this is in frequency domain. You can, to understand this example is actually, because this is in frequency domain, and this frequency domain is covered in test 2. So it will be very important to understand this example, okay, because we will do the magnitude and phase. Test 2, maybe you won't have, the phase system is not covered, but the magnitude response is actually covered, right? So let's do this example. So let's say we have two input signal. Let's say x1n, which is equals to cos 0.5 pi n. And so let's say the n is actually starting from 0 up to 40. Okay, and then we have a x2n, x number 2, cos, sorry, this is not 0.5, 0.1, 0.4 pi n. Same range. So let's say we have a same range. So these are the two input signal, and then we have a filter. Let's say our filter is, we will do a linear phase. right? So this is a linear phase. So what we have is a 0.2, 0.2, 0.2, 0.2, 0.2. 1, 2, 3, 4, 5. This is index 0, index 1, index 2, index 3, index 4. Okay, so this is actually 0, 1, 2. So it is actually symmetrical at this point. But this is a delayed signal. This is a delayed signal. This is not an even signal where it starts at -2. So it starts at 0. So, but it's still a symmetry. So, but we call it a delayed symmetry. So what is this? So this is actually a linear phase system. Okay. So how many delays? What is actually the delay? Because if this is the center, so we are actually moving 2 samples, right? So actually the delay is the ND is a 2. So this is the ND. So we will try to find out. So what will happen if we filter X1 and X2? Okay, we filter X1, X2. So what will happen to the amplitude? The amplitude is actually here is 1. This is also, let's give a different amplitude. So let's say this is 0.5. Okay, the amplitude is 1, frequency is 0.1 pi, and this is the amplitude is 0.5, and then the frequency is 0.4 pi. Okay, what is the phase? The phase is 0. So we are assuming that our input signal doesn't have any phase, and then there is no delay in input signal. Okay, then we will see because this is a linear phase system, so we should see some delay at output. Okay, and what will happen to the amplitude? So will this 1, amplitude of 1, still be 1, or will it be reduced, or maybe it will be increased? Okay, so we need to check the magnitude. And this one also 0.5, will it still be a 0.5? Will it be reduced, or maybe it will be removed, right? So maybe it will be increased. So we need to check on this. So this is where we're going to do some analysis in frequency domain, so that we will understand what will this filter do. Okay, what will this filter do to this signal? So basically, we will have yn equals to whatever we have, x, n. We will do a convolution to hn. Okay, and then y omega. So we will have x omega multiplied by h omega. So that's what we'll have. Okay, and then if we write it in the phase and magnitude form, so this is actually E minus a j, phase of y omega, multiplied by magnitude of y omega. This is equals to E minus j, phase of x omega, and magnitude of x omega, multiply E minus j of h omega, h, the magnitude of the h. Okay, so we have this thing. So we should have this thing. So then, or we can do this. This is actually the sum. This is x, a sum, h. And then this is just magnitude. We do multiplication. Right, summation on phase, and then multiply on the magnitude. So then what is our, we will focus on these two frequency, which is a 0.1 pi and 0.4 pi, because we need to know what will happen to this amplitude. What will happen to the phase? Okay, what will be the delay at the output? So we need to focus on these two frequencies, 0.1 pi and 0.4 pi. Okay, so first let's find what is actually h omega. So first, we need to find this h omega. Okay, we should do that. And to do that, we know that this h omega, actually we can do is we do this 2 omega of the even, because we can have this as an even version of this one, which at center it will be 0. Because why we do this? Because we can use the formula for symmetry. Because there's a DTFT properties on symmetry, the symmetry properties. So because we know that this H even, because it is easier to use that formula, because the result will be just on cos, and then we just multiply by e minus j2 omega. Okay, rather than solving this, so it is easier to solve the even version of it, and then just multiply with e minus j2 omega, right? So let's do that. So we know that this h e omega, we can have h e omega equals to, so let's see if I remember the formula. See, I'm referring to the formula, okay, because you can refer to the formula in test and exam also, because it will be given. Let's see, I already print that. Okay, so for even signal, the formula is it will be h0 plus 2 summation of n from 1, and because our signal is this is a half of it, so then this is 1, this is 2, so then 1 up to 2 only of hn cos omega n, right? So this is our formula. So we solve this and then just multiply with e minus j2 omega, because the nd is 2 here. So then this is h0. So what is a h0? So h0 is, because everything is a 0.2, so this is 0.2 plus 2 of, we need to multiply this, 0.2 cos omega plus 0.2 cos 2 omega. Okay, do that summation, plug in the n equals to 1. So h1 is a 0.2, and then this is 1, becomes omega here, right? So when n equals to 2, so this is 0.2, still 0.2, because everything is a 0.2. So all values are 0.2. So h2 is actually 0.2 also. And then this n is now 2. So this is where we get 2 omega. Right, then we can, so this is a 0.2 plus 0.4 cos omega plus 0.4 cos 2 omega. Okay, so that's he omega. And to get our h omega, again, what is the h omega? H omega is just e minus j omega, 2 omega, multiply with the h e omega. And we already have that, e minus j to omega, multiply by 0.2 plus 0.4 cos omega plus 0.4 cos 2 omega. Cos 2 omega. Okay, so this thing, so we have, then from here, so it is easier, because we have seen from a previous example from previous class, this is where straightforward we can get our magnitude. We can just remove this, okay, and then take absolute value of the rest. So that will be the magnitude of a linear phase system. So what would you get is just a 0.2 plus 0.4 cos omega plus 0.4 cos 2 omega. So that is our magnitude response. So what is this? So this is magnitude response. So how about the phase response? So the phase response, so this is phase response. So and then the phase response is actually also quite easy, straightforward. So we have seen example from previous class that this is just whatever you have here. Okay, so this is a negative 2 omega. It doesn't need to do any calculation because for a linear phase system, so this is a delayed symmetry a system. So the phase is just whatever you have here. So you just remove that G. So it is a minus 2 omega. What is the magnitude? The magnitude is remove this exponent and then take absolute value of the rest. Okay, so this is what we have. So now we're going to analyze on the two frequency. So what will happen to this signal? So if the amplitude is reduced, then we can say that this signal has been reduced. If the signal is increased, then we can say that the signal has been magnified. Right? So let's see one by one. So do we need to plot this thing? So actually, we doesn't need to plot it because we have a very specific frequency. So what we are interested in is just these two frequencies. Okay, we doesn't need to plot it, right? Unless in test and exam, so the question asks you to plot, then of course you need to plot. So, and this is actually not that quite complicated to plot because we know what is the cos omega, very easy to plot. And cos 2 omega is also very easy to plot, right? And then just do the plus, okay? Plus both, and then you will get the magnitude response. All right, so at the first frequency, at omega equals to 0.1 pi. Okay, again, hopefully you don't get lost because frequency, we have 5 types of frequency. The original frequency is the physical frequency, so which the unit is in hertz. Okay, but in discrete time, signal and system, so because there is a sampling, so we have been introduced to 2 types of frequency. So one is the normalized frequency, which is in small f. The other one is the angular frequency, which is in the small omega. Right, in the continuous time, so we have a capital omega. Okay, so we are using this small omega now as our frequency. What is the unit of this one? There is no, the unit is just radian. So it's just a radian because this is angular. So we are using this one. So at omega equals to 0.1 pi, then we can have our magnitude equals to, because this is our magnitude, we just plug in the value. This is a 0.2 plus a 0.4 cos 0.1 pi plus 0.4 cos, this is 0.2. Okay, because this is 2 times omega. Our omega is a 0.1 pi. Okay, so I will let you do this. Okay, try to calculate this. What will be our h omega at 0.1 pi? So, and put your answer in the chat section. If you have any questions, so you can ask. Okay. So, but now please just compute this, so that you will move your hand, move your brain, so that's anyone? You can do this very fast actually. 0.904. All right, actually that one is correct. I already checked that. 0.904. Okay, so this is actually the correct answer. So at omega equals to 0.1 pi, so your magnitude is a 0.904. Okay, and the phase is simply minus 2 times 0.1 pi, which is negative 0.2 pi. And this is actually phase. This is not representing your delay. So what is a delay? ND. ND is actually equals to phase. So we have seen this formula before, actually. This one, actually, this is the delay. So you need your phase divided by your omega. Divide by omega. So this is where you will have minus 2 pi divided by 0.1 pi, which is equals to 2. Okay, so that's why we have this 2. Okay, now what will happen to this signal? So the amplitude actually will be multiplied by 0.904. Okay, so let's try to draw these signals. 0.1 pi. So how do you sketch this signal? So we're going to look at. Okay, let's sketch that. Let's have the signal again. So this is a cos 0.1 pi n for 0 up to 40. When we look at this frequency 0.1 pi, so this is actually representing omega 0.1 pi. And this is actually equals to 2 pi f. Right? This is a normalized frequency. And what is our f? So automatically we know that our f is actually equals to 0.05. Okay, that's the f. 0.05 multiplied by 2, so you get 0.1 pi. And what is this? So this is actually if you have a signal n, and this is cos. Okay, one cycle. So this is actually one cycle. So that if we have, let's say, so what is, let's say this is our TP. So the period or number of samples. So how many samples we have here? Okay. So actually this is from, because we know that f is actually equals to 1 over that TP. So what is a TP? TP is just the other side, which is 1 over 0.05 equals to 1 divided by 0.05 is 20. So it means that if you have n equals to 0 here, so you should have n equals to 20 here. And this is 40. So you have 40 over there. So we have a 2 cycle of this frequency, right? Because the range is 0 up to 40. So the other one, which is 0.4. For omega equals to 0.4 pi, which is, this is equals to 2 pi f. So the f is actually equals to 0.2. And that 0.2, that TP is actually equals to 1 divided by 0.2 is 5. Okay, so is it correct? 1 divided by, hopefully I'm correct. So I can do it with that's simple. 1 divided by 0.2. Okay, 5. Right. So it will repeat every 5 samples. So if you have 20 samples here, so now it will repeat by 20, so maybe this is 10, so this is 5. Right, so hopefully you can see the sketch, but the frequency is higher, and actually I'm doing this wrong. Let's see, let's Control Z on that one, because the amplitude of the second is a 0.5. Okay, so it's supposed to be half of that. Right, and then of course you can continue until 40. So this is actually x1, this is x2. Okay, so this is the signal. So let's see what will happen at the output. So the first thing is this is 1, this is 0.5. And we already know that for the first signal, so the amplitude will be reduced. So what's left is actually something like 90.4%. Okay, or this is simply as a 0.904 multiplied by 1. So now the amplitude will be, this one will be reduced up to 0.904. Let's draw that again. So this is 20. So this is 40. And the original is 1. And what we know, the delay. So the delay is 2. So our signal is supposed to be delayed by 2, and the amplitude is actually reduced to 0.9. And if you want to delay this by 2, so this is where supposed to be, let's say this is 40, 30, so somewhere. So maybe this is 22, and this is, let's say, 2. And it should be a little bit less. Right, so this is actually this is the output. So this is the input. This is xn, x1n. So this is let's say y1n. So if this peak is at 20, this peak is at 22. So this is actually this is the output. So delay by 2 and reduce to 0.9. 0.904. Okay, so this is what happens. So this is what the filter do to our first signal. So what is our filter? The filter is a 0.2, 0.2, 0.2, 0.2, 0.2. So what does it do to the first signal? It will reduce the amplitude into 0.904, and it will delay. It will delay the signal at the output by 2 samples. Okay, so let's move to the other one. So which is the second one is on 0.4. So at omega equals to 0.4 pi. So then we can have our h omega magnitude equals to 0.2 plus 0.4 cos 0.4 pi plus 0.4 cos 0.8 pi. Okay, now let's calculate this one. What should you get? 0.2 plus 0.4 cos 0.4 pi plus 0.4 cos 0.8 pi. Okay, why we do that? Because we are now moving to our second signal, so which is the frequency is 0.4 pi. So let's see what will this filter do to that signal. And while you are doing that, the H omega is the same. All right, so Jason says that it is a 0. Yes, that's correct. It is 0. So what will happen to the second signal? So means that if y to n is actually equals to x to n, x number 2, convolved with hn. So we know that this is, the amplitude is originally 0.5. That 0.5 multiplied by 0. Okay, 0.5 multiplied by 0. So then it will be 0. Okay, so this is actually just 0. Okay, because the amplitude is 0. So the amplitude at output is 0. So this delay, so which is actually this one, nd is equals to minus 2. So of course, this is not no more significant because the output is actually just a 0. Okay, so nothing left. So nothing left on the second signal. So this is actually what happened if we do filtering on this one. Okay, so but why we do this? I'm giving you this example separately because we want to analyze one by one the signal. But of course, in real signal, so all these frequency are normally it is in one signal. It is in one signal. So if we are let's say assuming let's say we have a x3n equals to x1n plus x2n. Okay, this one. So this is actually, so then x3n have a two frequencies. So one is a cos 0.1 pi n plus 0.5 cos 0.4. And this is for 0 up to 40. Okay, we can have this thing, x3n, which is the combination of x1n and x2n. And if you want to sketch this signal, so we already know that. So we have these two signals. So this is x1n, the lower frequency. This is 0.1 pi. This is a higher frequency, so which is a 0.4 pi. Okay, so and it is actually a bit clear here because in one cycle, this is 0.1 and then this is a 0.4. So this is one cycle. So then that 0.4 have, of course, a 4 cycle. Okay, so if we look at that one, if you want to sketch x3, 0, 20, 40, let's say this is, we divide that more because we should have that one. And maybe your signal will be something like because I need to, okay, this is a center. This is the center. Because originally, let's have some base on the lower frequency first. Oops, that's why I get it wrong. Okay, when you add that higher frequency, so I'm going to change to a different color. So then maybe we should have something like so here. So it becomes something. Okay, when you add those two frequencies, so that rate signal, so it's not a smooth signal, right? So it's not smooth. So you can see that because after it mix, because the first one is a lower frequency, the other one is a higher frequency. So this is where at output, let's say this is X3 and this is Y3, and so we know that this higher frequency will be removed totally, right? Because why? Because the magnitude at 0.4 pi is actually equals to 0. So when it is equals to 0 means that the amplitude will be multiplied by 0. So remove. But then the first one, the lower frequency, so it will be reduced to 0.9. So it will reduce to 0.9. And it will be shifted by two sample. This is 22. This is 10. It's supposed to be 12. Okay, this is 2. So we'll start here. And then we'll end somewhere here. And then this is and what will be the amplitude? 0.904. Okay, so this is actually the output. So originally we have a mix of two signal, and then because our filter will totally remove the higher frequency, so what's left is just the lower frequency. So this is a 0.1 pi frequency. But the position is not on the original position. It doesn't start at 0 because it's being delayed by two samples. Okay, so that's what happened here, right? And yes, please focus on this because this example is very important for your test too, and also for final exam. So because in final exam we have questions on phase also. So this is, but the coverage is until zero phase and linear phase only. So I'm giving you a hint actually. Right, so because what we have developed is actually this concept of a filtering. So after filtering, what should happen? Okay, at the output. So what will happen to the amplitude? What will happen to the position? So is it being delayed or is it not? Okay, and we're not covering the non-linear phase. So whatever you will have in what we covered in this linear phase system, so everything will be delayed on the same delay on every frequency. Okay, so we have seen that example. And as a reminder, so our test 2 will be this Thursday at 5 p.m. Okay, so hopefully everybody are aware of it. All right, so actually that's all for today because we have finished that example. So this is our last example. So we have seen that this is an example of how we do filtering by a simple filter. So actually that one is a simple filter. We just have 5 samples on the filter and everything is a 0.2, 0.2, 0.2, 0.2, 0.2. But on this a signal, so it can do the filtering. Okay, so any question before we end the class today? And yes, make sure do your assignment starting next week. Okay, but if you want to start early, you can already start doing the assignment. So, okay, all right. So if there is no questions, so and before I forgot, there will be no class this Thursday, so that you can do your preparation on the test too. Okay, no class on Thursday. So we will have a class next week, and next week we will start on what we call a discrete Fourier transform. Okay, which is another very important topic, because the FT is the one that we are going to implement. Practically, we are implementing the FT, not DTFT. DFT is just a conceptual. All right. Okay. So that's all for today. So see you guys again this Thursday on test 2.
Doctor, I got a
Yeah.
question.
Yes.
Can I share my screen?
Yeah. Sure.
Uh, so,
Let me stop. Okay.
so my question is for this question. So, my concern is how did it get this equation from this? Because since from the Euler's formula, it's in that ej omega it's equals to cos omega plus j sine omega. But I'd like to know where how we can demolish the j and to form an equation like this.
Okay. Is that it? Is that the question?
Uh, then the second part is I did try it out using the multiplication of ej omega, but apparently the answer is a bit off. I will take a picture and share in the group.
Okay, while you are searching, when we do a magnitude of phase, okay, so actually we are taking the value. So the value of real and imaginary. When you take the imaginary value, of course you don't take that j. Okay, because real and imaginary is just if you are imagine it as a on axis. So you have one axis on real, you have another axis on imaginary. Okay, so actually you will not take that j into consideration. So it's just a representation saying that j is actually representing imaginary. So this is when you do a magnitude and phase calculation. So you just take the value, don't take the j. Okay, the real, you just take real, no problem because there's no j. The imaginary parts, do not take that j.
Oh, okay, but
All right.
I did share my solution in the WhatsApp group, but my concern is regarding the sign because the answer provided it's a plus, but I'm getting a negative sign there. So is it my problem or?
Wait, I'm looking at it.
Ah,
So ej omega, that one, and then so which sign?
mean at the final part where the cos omega plus cos 2 omega squared, the provided answer is a plus, but I'm getting negative sign instead of plus.
That negative j sine omega. You mean that one?
Yeah.
J sine 2 omega minus j sine. So with cos j. Okay, let me share the screen. Okay, so which one that you mentioned that negative? This negative?
Yeah.
So okay, what should you do is actually identify which one is the real. So this is a 2 cos omega, right? Plus cos omega, and then minus j 2 cos omega, and then so actually this is the This is the real part, no problem, because everything is in positive, so you do the square, right? And then for the negative, for the imaginary part, so this is a 2 cos omega sine omega. So you can bring out the negative in front. So this is actually what you did here. J sine 2 omega. Is that 2 omega? This one. Minus minus, so this one's supposed to be, actually what should you do is just bracket everything and then square. Okay, this is something wrong here. So this is just actually plus, and this is where you need to put a negative in front. Okay, everything. So this is plus. This one's supposed to be negative in front, and this is the negative because you have negative there. And then solve that, and then square it. Remove the j. Okay, remove the j. So it doesn't need that j because we are just taking the value, not the j, because j is just a representation of imaginary. Okay, we don't take that one. So remove j, remove j. This is plus, and you should have negative in front over here.
Okay, all right, got it.
Okay, and then you should solve that. So I believe you will get the correct answer after that.
Okay. Thank you, Doctor.
Okay. So any other questions? So this is a good question because we are focusing on a symmetry signal, right? You should focus on this one. Okay, ada lagi ke? So any questions? Any questions? So don't be.
Can I ask another question?
Yes, yes.
It's out of our topic, but so let me share screen again. So the second question would be this one. So I'd like to know how they get this like arctangent 0.25. Like how they get it. This is from the last year question from the 2020 2021, I guess.
Okay. So can you scroll up a bit? What is the full questions?
I will send the one I got it in the group again. It's question number 2.
Okay, wait, I'm opening it.
I just want to say these are good questions, and thank you, Jason, for asking them because it's very informative.
Question number 2.
Number 2C.
2C. All right. Okay, so this is the question, the pole zero plot. Okay, so this is the pole zero plot. Is shown in the figure below. Dotted blue line indicates the unit circle. Okay, that one is the unit circle. So we have 2 zeros, and then we have 2 poles. Okay, the first one is a FIR, and then B, obtain the system function Hz, and then C, briefly sketch the magnitude response, H omega, for the above system. Note, just sketch in the range of 0 up to pi. Okay, so this is actually half plot, right? If you realize, we have 3 types of plot. One is a whole plot, the full plot, half plots, and then shifted plots. So this is actually a half plot. So what is the answer? The answer, using the fact that a 0 contributes a valley and a pole contributes a peak, we can simply sketch the magnitude response as follows. And actually this is covered. Chapter 9. covered here, frequency response related to poles and zeros, which is actually we didn't cover this semester. So all the story is actually here. So how we can estimate magnitude response based on poles and zeros. Okay, because actually basically so what we do is actually how do we estimate zeros will actually push your magnitude response to a magnitude of 0. Okay, the closer these zeros to unit circle, so the magnitude will be closer to 0. So that's the fact. And then poles, oppositely, the closer the poles to the unit circle, so you will reach to infinity of magnitude. Okay, so then this is somewhere maybe what is the frequency here? The frequency is we are looking at the angle, because this is the omega from 0 pi. This is pi over 2 pi until 2 pi, right? But we are looking only from 0 up to pi. So this is somewhere, if this is pi over 2, this is pi over 4. So maybe this is 0.1 pi. Maybe, okay? Let's just estimate something. And this is 0.5 pi. So this is somewhere maybe 0.7 pi. Something like that. So this is where we're going to have somewhere there. So this is the one that we estimate, almost a 0.1. This is almost a 0.7, which I just mentioned. But accurately, this is a 0.665. We can compute that from here. What is the angle? The angle or the phase is just tangent inverse of 0.2 divided by 0.8. So this is the angle. What is the angle of this one? Tangent inverse of that 0.7 divided by minus 0.4. Okay, because we are looking at the angle. Right? So, but yes, I didn't cover this thing this semester. So, what is the good news? You won't have this kind of question in test and exam. But actually, this is what we do. So, poles is here. So you will see a very high magnitude. And zeros is here. So you will see a very low magnitude. Right? And this is just a sketch. So I already show you how to get this 0.078 tangent inverse of that imaginary divided by real. Okay. Then whatever it is, this is just a sketch. So some low value here, some high value over here. And then because later, when we go for a filter design chapter, so we will see that, I think this one, maybe the cutoff frequency is somewhere 0.5 here. And then we will have a fixed value at 0.5 at cutoff frequency. All right, so, but that one is later. But what should we see here is just high value on poles, low value on zeros. Right? So any shapes that you do, because this is just a sketch, you have a low value here, high value here, you will get it correct because it's just a sketch. Okay.
So, okay, sorry, like as you mentioned that it's imaginary divided by poles, right?
Yes.
It's imaginary value divided by real values. But for the poles, if I divided the imaginary by the real values, I'm getting a different answer. I'm getting 7/3 instead of 4/3.
Because this is on the second quadrant. Okay, you need to be careful on that one. Doing a tangent inverse, so there's a bit different on the first quadrant. This is on the second quadrant. This is on the third quadrant, fourth quadrant. All right. So maybe you need to do some revisit on how to do tangent inverse on this fourth quadrant, because trigonometry, this is a bit complicated, right? So I think before this, you guys already have some mnemonic on how to memorize that. Okay, so 0.4 and 0.7 here. So what is actually the angular here? So it can be represented by this one. So what is that theta? So it must be more than 0.5. Of course, if you do a straight divide, 0.7 divided by minus 0.4, you won't get above 0.55. Okay, there's a trick on how to do that. I don't remember how to do that, but there is a trick on doing that. All those 4 quadrants. Okay, but luckily you won't have this kind of a question this semester.
Thank you, Doctor.
Okay, clear. I hope you try. I hope you try, because this is how to get this quadrant and this quadrant. What is the difference, right? So that's the hint on how to do that. Any more questions?
Not for me.
Mm-hmm. Yeah, very good. Thank you, because asking questions, because I'm sure all of you have a lot of questions. But to ask the question is another challenge. Okay, so whatever it is, if you have any question, you can PM, do a private message to me, or just go to this WhatsApp group, our WhatsApp group, share your questions, and then I will try to answer it. Okay, I will try to give you the how to solve it, so that we can learn together. Okay, because that's the idea of learning in a class. You are learning with your friend, not alone. Okay, even though you are on yourself at your home, but actually we can connect to each other. All right, so good luck for test 2 this Thursday. Okay, so I think that's all for today. So assalamualaikum warahmatullahi wabarakatuh, and good afternoon to everybody. All right, so see you guys then next Thursday. Okay, bye everybody.
Waalaikumsalam. Thank you, Doctor.